was due, but we didn't say that we were handing it out Friday. So because we had 2 snow days, and I know you're going to go, hoo, 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 we have to give you the quizzes as take-homes instead of in class. So it's actually, there's some, yeah, like you like that, right? Okay, cool. I know, darn. So, and now I'm going to be very specific and make this statement today. So on Friday, be here or get a 0. Be here to pick up your take-home test. Your take-home, yeah, your take-home quiz, excuse me, quiz number 2. So I said this before. I'm going to say it again. If you are not in class, it's just like you're not being in class the day a quiz is due. So if you're not here on Friday, don't email me and say, sorry, I didn't make it to class. Please email me my quiz. If you're not here, then it's going to have to be the one that you drop. Okay. Well, there's not going to be a snow day on Friday. Because I've said no snow on Friday. Yeah, then we'll have to do, I don't know, maybe the test would have to be take home. No, that would never happen. Okay, also don't forget your first project, your GeoGebra project is due on Friday. Some of you have already handed it in. Put it in those blue folders because you know, this was assigned like weeks ago and some of you just went ahead and did it and threw it in the folder. So that's fine as well. So those are the 2 things on Friday. So today we're going to expand our horizons, which is our number system, and we're no longer going to just be dealing with real numbers, which have a home on the number line. Every real number has a home on the number line. Did that go on? It's coming. Okay. We're now going to start dealing with numbers that at first are a little strange to think about because they're not something that you find in your heart and soul. They're not intuitive. You can't count out this number. Okay, so it's very strange at first, but mathematicians invented this number to help them solve equations that they had no way of solving. And this number is the number I. And that's a symbol we use for it. And the definition, just like if I said, what does Schadenfreude mean? Right? If you don't know, you'd look it up in the dictionary or you go on Google, right? Nobody has a dictionary anymore. I keep forgetting. You go on Google, you'd put it in, you get the definition. The definition of I is equal to the square root of -1, which we've never, with real numbers, every time we get a negative number under our radical sign, that as long as it's an even root, square root, 4th root, 6th root, we say we can't do it. No can do. And hey, we got out of life easy, right? No more. We've now got to deal with a new number system, and we'll talk about that in a second. But for now, whenever you see the square root of -1, it's going to be defined as the letter I, or the number I. The letter I is used to symbolize this number. Okay, so let's suppose you have something a little more complicated than -1 under the radical sign. Let's say there's another number like here, -49. Well, all you do is you break up your negative radicand, that's what we call the thing underneath the radical sign, so that it's the square root of -1 times the square root of that number. And then all you do is you replace the square root of -1 with I, and then the square root of that number. And that's it. Sometimes we can simplify that radical, sometimes we can't. So let's take a look at the square root of -49, and let's apply this idea right here. So the first thing you're going to do is you're going to factor this into 2 radicals. And the first factor is your -1. And what's your second factor going to be if you follow this little, not 47. What's, yep, 49. And we replace the square root of -1 with the letter I, and we replace the square root of 49 with 7. Now you can either write it in that order, but typically we put the real number in front of the imaginary number I. It doesn't matter because the order of multiplication doesn't matter, but this is typically how you find it. Okay. So what about B? B is square root of -1 times the square root of 8, which is I times the square root of 8. Now, if I couldn't simplify the square root of 8 anymore, this is how I would write it. The reason I put the I in front now at this point is because sometimes if you scoot it over to the right, it's not clear, like, where are you putting it? Sometimes people are sloppy in their the radical symbol goes out like this way, and it's not clear where the I is. But we can simplify this a little more, and that's, you did this practice in your preview exercises. So this is 2i square root of 2. That's how we would simplify it, because this is the square root of 4. Square root of 4 is 2. 2i times the square root of 2. That's what's left. Okay, so we got 7i here. Let's, we'll check this in a minute, but we have to look at this property in order to check it. So if I is the square root of -1, and I square both sides, oh, if I square both sides, I'm going to get I square. What happens when I square a square root? What happens? They cancel each other out, because squaring something and square rooting something are inverse operations of each other. They're inverse operations. They undo each other, and what you're left with is what's right underneath, the -1. This is going to be a very important property of this number that you need to have in your head, because we're going to use it over and over. So I square, whenever you see I square, it's going to equal -1. You can replace it with -1. So let's see if we check this. If I take the square root of a number, then I should be able to take my answer and square it and come right back to where I started. So I said the square root of -49 was 7i. So I should be able to square 7i and get -49. So because I have multiplication inside these parentheses, I can use an exponent property. And that exponent property says I get to square my first factor and I get to square my second factor. 7 squared is 49. And we just learned that I square was the number -1. And there's your -49 back again. Okay, so the I square equaling -1 is going to help you check your square roots to see if you've done them properly. Nope, I'm just showing it to you, just so you can see. Nope, you don't have to do that. Unless you're worried and you want to make sure you did it okay. All right, so let's move on. We're going to do some, we're going to talk about the number system that gets created now. If we take all our real numbers, and you look at how I've represented real numbers here, a plus bi, and you're waiting, what? I never wrote a real number like that, but notice what it says, b is equal to 0. So notice, it just looks like that, a. That's a real number. But we can put it in the form of what we call a complex number. A complex number is made up of a real part and an imaginary part. And it has this form. A and B are real numbers. They could be numbers, nice friendly numbers like 3 and -10. A could be the square root of 9 or square root of 11, square root of any number, negative square root of 2, could be pi, could be any real number. A or B can be any real number. But notice when B is 0, we just get in simplified form our real numbers as we know them. Okay? So the complex number system is made up of 2 sets of numbers, the real numbers and the imaginary numbers. And when we put those 2 sets together, we get this much larger set called the complex numbers. So we can do arithmetic with complex numbers just like we would do any arithmetic problem. Now, don't be fooled. A lot of times students see a problem like A. This happened in right after my 840 class. One of my students went in to do his my math lab homework. The minute he sees these parentheses, what does he think in his head? Multiplication and the distributive property. And I said, well, what's that big sign, that operation? Oh, Linda, I didn't even see that add sign. So when you're asked to add 2 things, in this case, you can just drop the parentheses without being arrested. Okay, and there's your addition property. There's your addition problem. So the order of addition doesn't matter. So we usually do this part in our head. We usually put the like terms beside each other and we combine them. 2 and 1 are 2 real numbers. When I combine them, I get 3. And 3 i's and 5 i's make 3 plus 5 or 8 i's. So the arithmetic is just like it's always been. Okay, you just add the like things together. That's never going to change, whether you're doing an arithmetic problem, an algebra problem. They always got to look like. Fractions, they always have to have like denominators. Same is true with subtraction, although now when I drop this second set of parentheses, I have to subtract both of the things inside or else I will be arrested. Okay? And there you see 2 take away 1. When I combine that, I get a 1. And 3 take away 5i gives me a negative 2i. So you're going to like adding and subtracting these because it's really not any different than if you had 2 plus 3x plus 1 plus 5x. It's just now called an I. Okay? You've been doing this for a long time in your life. All right, now how does D and A differ? How does D and A differ? Yeah, D is a multiplication problem. So here you use your distributive property twice. You say 2 times 1 and 2 times 5i, and then you do 2 times 3i times 1, okay, and 3i times 5i. You have to do 4 multiplications here. So you do 2 times 1 is 2. 2 times 5i is 10i. 3i times 1 is 3i. And 3i times 5i, help me with that one. No, not the simplified answer, just 3i times 5i. 15, because 3 times 5 is 15, and I times I is I squared. Okay, so you say, can I simplify this at all? Well, I can't simplify 2. 2 is always going to be 2. But I notice here that these terms are like. They're like. So I can put those together and get 13i. And then 15i squared, you may think, I got to write it as 15i squared, but then you remember that little secret that I squared is negative 1. So you replace I squared with negative 1, and that becomes negative 15. So lo and behold, you have 2 more like terms right here, your 2 constants, your 2 real numbers, and you get 13i minus 13. And you're all set. Okay, any questions on that? And like I said, in your homework, you'll have some questions that will help you with this. Okay, another multiplication problem. What's so special? Why would we just did a multiplication problem here in D. Why would I give you E? What do you think's going on in E that makes it so special? Why do I bother giving you another multiplication problem? The I, there's going to be something that cancels each other out here, right? The middle term is 2 times 3i is a 6i, and then 2 times negative 3i is negative 6i. And when you add those, voila, a nice big fat 0 comes out. So you're only going to end up with 2 parts to this expression, 2 parts, 2 terms. It's either going to have a plus in between or a subtraction. What is it about these factors that makes that happen? Kira, can you help me with that? Do you know why we get that cancellation of the 6, that it goes to 0? What's special about those factors? Yeah, they're basically, they look almost like they're identical twins, right? But these would be twins that were fraternal twins. They don't look identical because one's got an addition and one's a subtraction. So if the numbers are the same, the terms are the same in each factor, but one's an addition and one's a subtraction, there's a really fast way to do it. You just square your 2. You know, since the signs are different, it has to be a minus. You square your 3, and you square your I. But look what happens. That becomes 4 times 4 take away 9 times negative 1, which is 4 plus 9. So look at this. This turned into the sum of 2 perfect squares. Before in algebra, we said we couldn't factor the sum of 2 perfect squares, and now we're going to have an ability to do that. So we would combine this and just call it 13, so you wouldn't necessarily recognize that you got the sum of 2 perfect squares unless you looked at your work. So this is kind of a really neat thing. These types of factors are called conjugates of each other. And how you create conjugates is you simply change the sign from addition to subtraction or subtraction to addition. So we just saw that the conjugate of 2 plus 3i would be 2 minus 3i. and something magical happens. Let's look at the general case here so that we don't have numbers for A and B, but we just look at the general case. If we look at A plus BI times A minus BI, the A times A gives you your A square. A times negative BI gives you negative ABI. A times BI gives you a positive ABI, and I just write it right underneath instead of to the right of it. And then I get minus B square I square. This big thing goes to 0. Those two terms are opposites. They're manipulated that way to be opposites. And you get A square minus B square I square. I square is negative 1. So this becomes A square plus D square. It becomes the sum of two perfect squares. So if I now ask you to factor the sum of two perfect squares, you can. You just take the square root of A, and then you put plus BI minus BI. You just create two conjugates. And that's how you can factor any sum of perfect squares. So before, with just the real number system, you would just say it was prime. You could only do the difference of perfect squares. Okay, so why do we learn all this? We learn all this so that we can find solutions to quadratic equations that don't have real number solutions. That's one of the reasons we do it. So I think a lot of you have solved quadratic equations before. Let me just do this for you real quick because I want you to have time to work today. If you see a problem like this, you want to evaluate each one of these separately. Do not multiply them together. Do not multiply these and get the square root of 100. Okay, because this is not true. This does not equal the square root of 100. So you want to take each of these separately. It's the square root of negative 1 times the square root of 20 times the square root of negative 1 times the square root of 5. Right? And you have the square root of negative 1 times the square root of negative 1 times the square root of 20 times the square root of 5. Now these you can put together and call the square root of 100 because these numbers are positive. So this is the square root of 100. And the square root of negative 1 times itself is negative 1. So these undo each other. So my answer here is negative 10. So you'll probably have a couple of those on your homework to do. So just remember, do them individually and then simplify them. All right, so quadratic equations versus linear equations. Okay, linear equations are called first degree. Quadratic equations are called second degree. Now, this terminology or this language may be new to you, but if you look over those examples I gave you, can anybody figure out why we might call linear first degree and why we might call quadratic second degree? Any ideas? Yeah, Clay, what do you think? The exponents, right. So if you look at any linear equation, even though you don't see it, what's the highest exponent on any variable you see there? 1. It's not there, it's understood to be there. So that's where the word first degree comes from. And on your quadratic, you can see the highest exponent in that equation is 2. So these are examples of polynomial equations. We're going to work with polynomials for probably a week and a half later on. But polynomial equations are equations that are really nice because all the exponents are nice positive integers. You don't have fractions, you don't have negative exponents, so they're really easy to work with. So these are examples of polynomials. Now, this is how we define a general quadratic equation, and notice we always have to put this a does not equal 0 on there. Why? Why do we have to say a, b, and c can be any real number in the world, but a can't be 0? Why do we make that statement? Just because we want to make it more complicated looking? What do you think? Yeah, if a was 0, this whole thing would go, and you'd have a linear equation. You wouldn't even be solving quadratic then. All right, so look, I'm just going to give you a little table, which is not on here. Oh, I haven't showed you the comic yet. Oh, that's right, I forgot. So here, has anybody noticed on the GCC website, there's one of the pictures that comes up is of this, a big face. It's just one big person's face. She's got dark hair and big glasses on. Anybody notice that person on the website? That's how someone described it to me. All right, it's not that picture. Can you make these go from the next one picture to the next? Or you just gotta wait. Okay, here she's coming next. Come on, hurry up so they can see you, Cecily. There she is. That's Cecily. Okay, Cecily was one of my 107 students about a year and a half ago. He's Jay Gump. He teaches anatomy and physiology. Okay, so Cecily has graduated from GCC. She's now at Mount Holyoke, and she's a math major of all things. Can you imagine? So she loves finding cartoons and sending them to me. So I thought today this would be a good cartoon to show you. If I can make it bigger. Let's see. I don't know. I had it bigger. I don't know why it's not getting big. Let's see. Oh, I don't want that. All right, maybe I'll just have to. Can you see that without? Can you see what it says? Just, you know, the typical psychotherapist here. Who's lying on the couch? Square root of -1. And what's the square root of -1 fretting about? Do I really exist? Yes. I got a little chuckle. All right. All right. It takes a lot to get chuckles today. In the old days, I could get lots of chuckles, but geez, you see everything now on videos and everything. So it's hard to make life too exciting for you. All right. Now, your typical quadratic formula looks like this. Equation. Ax squared plus bx plus c equals 0. We can take terms eliminating parts of this equation. Like we could have this type. We can let b be 0 and we're okay. Remember, our only rule was a couldn't be 0. We could drop c out, the constant out, and you could have an equation that has these two terms. And then, of course, you can have the full-blown equation with all three terms. Okay? And what I'm trying to do here is summarize the technique for you. Okay? The technique is, one technique for solving quadratic equations is a quadratic formula, which works all the time for any equation, no matter what it looks like. Okay? That's a cool calculator. Is that an app?
No, I don't know.
It came with the phone? Yeah, mine is pretty crappy on mine. I'm always looking for good calculators for my phone. Okay. iPhone, yeah. Okay. So do you see what I've done here? In this first equation, I've dropped off that middle term bx. In the second one, I dropped off the constant. And in this one, they're all three there. Now, so the moral of the story is, if you know the quadratic equation, it doesn't matter. You can solve any quadratic equation in the world. The problem is, students can mess up with the quadratic formula. I meant to say the quadratic formula, sorry. Students have trouble with it. They multiply things wrong. They add and subtract things wrong. They simplify things wrong. So I just wanted to show you a couple of examples where you could get out of it a little easier. In fact, I want to show you an example like this, because the middle one, because that one is like easy peasy. Let's suppose I gave you that quadratic equation. So the first thing, if you're trying to categorize these in your mind, you might say, hey, that's not the full-blown quadratic equations because I don't see my constant term c. I don't see three terms on the left side. So that's a clue that it may be one of these methods where you can do it a little simpler. Anytime you have your quadratic term, listen to my language, quadratic term, it's quadratic because it has an x square. It's a term because you have plus. And your linear term, linear because the exponent on the x is 1. You have a built-in friend, greatest common friend. What is it here? What's the greatest common factor here? 5x. So you can factor this immediately like this. And now this is going to be very easy to solve because this looks like the strategy we use to solve any quadratic equation, which is called the zero product principle. If you can write your equation, your expression on the left side as a multiplication problem instead of adding or subtracting, then you say if either one of these factors is 0, then the whole thing's 0. So once you have it factored, you take each factor, you set it equal to 0, and voila, life is good because they're little baby linear equations that you could solve in your sleep. And there are your two answers. Okay. The other thing you should be keeping your eye out for is that 2 tells you that it's quite possible to have 2 solutions. The only time you get one and it's an identical twin is when you have a perfect square. So there's always going to be 2 on some level, whether they're the same or they're different. So if you were doing this in MyMathLab, remember how MyMathLab wants you to put your solutions in a set? There's an order to put in these answers. You always put your smallest number first, so that would be -2, and then 0. So that's the solution set for this type of quadratic equation. All right. Now, if you have a quadratic equation that looks like this, which is the first one on your sheet, if you go back to your sheet here, to your class notes, that's this one, okay? And I'm just going to go forward here. Let me get rid of that. I don't need that blank sheet. Let's get rid of that. Delete. So notice this has this form because you don't have an x term. So it's missing something too. So if it's missing something, maybe there's a shorter way to do this. I'm going to show you 2 ways, folks. You add the 25 to both sides. So you get your quadratic equation set equal to 0. And now you say, yeah, Kavanaugh, what am I supposed to do now? I can't factor that. And the answer is, yes, you can. You can factor the sum of perfect squares because you now have I available. You just create 2 factors that are called conjugates. And what do they look like? X and x, plus and minus. And instead of just 5 and -5, it's 5i and -5i. And there you go. You have factored it. And now you set each factor equal to 0. And the only difference in your answers is one is plus 5i and one is -5i. You can just write your answer like that. Plus and minus 5i. That's what makes each one of those. -5i will make this first equation equal to 0, and positive 5i will make the second equation equal to 0. So that's one way, folks, so that you never forget that you have 2 answers. The second method I even hate showing you because students only do half of it. So typically what students will do, what would you do if you saw this equation like that? Yeah, you take the square root, and if you took the square root of x squared and really wrote it down what the square root of x squared really was, I wouldn't have a problem. But once you do this, you kind of set yourself up a little bit. So the answer to this is 5i. And the answer to this is really this. And this is the part you leave out. You've probably never seen that because your teacher along the way has allowed you to just write x. Let me make this, I just want to change this for a minute. Let's make this like this for a minute because I want to show you. So we know it's going to be 5i and -5i. But if you had this is really where you can get into trouble. You throw that thing over each side, that radical symbol. This says, what's the positive square root of 25? That's all it says. And that's all you're going to think about. And you're just going to write a 5 there. And because you were never either taught or asked to do this, the square root of x squared is not just x. Because you could have something like this, or you could have something like this. The answer here in both of these cases is 3. We know that. But this is the absolute value of what you're squaring, because we know our answer has to be 3. So in both cases, it's the absolute value of the base, whatever your base is. And since your base could be a positive 3 or a negative, this is really how you have to write it. It is the absolute value of x, because we don't know whether x is positive or negative. In our minds, we make believe it's positive, but x could be positive or negative. So to ensure that when it comes out, it's positive, you have to put the absolute value around it. If you do this step, then you know there's 2 numbers you can put in that absolute value sign whose absolute value is 5. Because there's 2 numbers that have a distance of 5 units from 0. What are those 2 numbers? 5 and negative 5. If you do this step, you'll remember that you have 2 answers. If you don't do this step, what you're going to do is you're going to put an X here and a 5 there, and you're going to forget that it's plus and minus. I've seen it. And I told my first class I'd do whatever I could. I'd get up there and do a tap dance on the table and sing to you if I could guarantee you would never forget the plus and minus. And that's because of this right here that nobody has either asked you to do or you've seen before. Yep, Amber?
Well, how come, why is it that the left side it's x equals plus or minus 5i, and on the right side it's only x equals plus or minus 5i?
Well, I changed the problem. See, I changed it to 25. That's why I changed it. So I could show you that method. It's a little easier with numbers instead of throwing the i's in. So let's go back now to the x squared minus 25. All right, real quick. So again, it's going to set you up a little bit. You're going to get set up a little bit because the answer here is really 5i. And if you don't think of this as the absolute value, you're never going to remember to write x equals plus or minus 5i. I see it all the time. So usually I don't do this here. See, I don't even put that square root sign. I say if you have an equation that looks like this, write the x here, and the first thing you should write on the other side is plus or minus. And then you take the square root of that, which is 5i. Putting that little square root sign over both sides is really what kind of gets you set up. This method is called extraction of roots. I even hate the name of it because it reminds me of the dentist's root canals. This method here, you use your greatest common factor. And then over here, you can either factor or use the quadratic formula. Okay. Hand up there, Ashlyn.
So you want us to write x equals plus minus, it's not the absolute value?
Oh, if you want, I would love it if you put absolute value in and then did, oh yeah. Then you'd really know why it was plus or minus, yeah. And you'd convince yourself a little more. So I'm just trying to make sure that you write your answer as both positive and negative, yeah. Yep. Okay. So quadratic formula would be for equations you couldn't factor, because if you can factor it, why go through all the agony of the quadratic formula? Some people don't think it's agony, but when I watch some results, it feels like it's agony. So let's see. So we've taken care of this one. I'm just going to show you here real quick because I want you to have time to work. This looks just like A, well, with a little twist. You have a square, a perfect square on one side and a constant on the other. So this is still missing. It looks like that. It's still missing that middle term right now. And the way to simplify this is to divide both sides by negative, to do it quickly. Divide both sides by -2. And now here's your perfect square and here's your answer. So if we skip all the absolute value and we skip using that square root side, if I find the square root of this, then x minus 7 is either going to equal the positive square root of 10 or x minus 7 is going to equal the negative square root of 10. And those are the 2 equations I have to solve. X equals 7 plus the square root of 10 if I add 7 to both sides, or x equals, excuse me. What am I doing? Hang on, sorry. Oh, just cross it out. All right. So let me show you what your tendency is to do here. When you see something like this, because it's not a single thing like x squared or a squared, what's your tendency? What are you going to want to do? Yeah, intuitively, oh, I hope you don't make it x squared plus 49. Why not, Dean? Why don't I want you to make it x squared plus 49?
Well, I know what it would come out to.
Yeah, well, tell me what it, no, what's it mean to square this the long way? What would it look like?
It means to multiply it by itself.
That's right.
Square it.
Yeah, that's right. So what would we get when we square? Notice, no multiplication in there, no division. Stay away from thinking that it's the exponent properties. There's adding and subtracting in there. It's a whole different ballgame. You've got to write out what it means to square it. So a lot of students get here and they don't think of square rooting both sides. They write the whole thing out like this. And then they subtract 10 from both sides, and now you have to use the quadratic formula to get your answer, okay? Or you can say, if I square root both sides, I get plus or minus the square root of 10 on the other side, and now you just add 7 to both sides. And there's your two answers, okay? So don't allow yourself to expand your view of things. You can have a perfect square and have the base be more than a single thing like x, or w, or b. It can be a quantity that's two terms. You can still undo it by taking the square root and remembering that you have both plus and minus square root of 10 on the right side. Because you could have put this in absolute value. The same thing works, the same technique. All right, I want to get to the quadratic formula. And unfortunately, okay, we've all seen how to solve one by factoring. I just did it for you earlier. So let's get to the quadratic formula because I want you to have time to work. You can only listen to me for a few minutes and then it's like, ugh. All right. So unfortunately, my little link here, if anybody can find me the tune that goes with Pup Goes the Weasel, I would be in your debt. So I could play I used to be able to play the song and we could sing together. So I'm going to sing the first round for you. Here's what the actual words to the song Pup Goes the Weasel are, and we're just replacing it with the quadratic formula. So here you can read the words to the melody. So here we go. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Ready? Together. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I don't think you're all with there. We got to do it again. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, if you put that on YouTube, some students have like put this to like hip hop music, but not Pup Goes the Weasel. They've done their own thing. And actually one year I had a class that said, we want to make up our own GCC version, and we never got it together, and I regret never taking the time because it would have been great to play like the version on YouTube. Clay?
I'd like to point out that lyrics all points. It was kind of like
Oh, yeah, right. I should take that exclamation point out of there. Thanks. Yeah, right here at all. See? All factorial. If you know what a factorial means, that actually has a meaning in math. Okay. So look, if I gave you an equation like this, remember, if you have all three terms, any two terms, doesn't matter. You can use a quadratic equation. If I saw this equation, I would factor it. I'd be done like that. I wouldn't go through the agony of the quadratic formula. So I'm going to factor it real quick. X minus 7, x plus 1 is 0. X minus 7 is 0. That means x is 7. X plus 1 is 0. X is negative 1. How long did that take? Just a few seconds. All right? But sometimes people have this thing about factoring because you just haven't had a lot of time to practice it. And you may have a little like, oh, I hate factoring, so you want something to help you. And people feel like the quadratic formula helps them. And that's cool if it does. All right. So the first thing you have to do is make sure your quadratic equation is set equal to 0, or else it doesn't work. And A equals 1, B equals -6 here, and C equals -7. Now here's my picky math teacher coming at you. All the steps you go through to go from this equation to this equation. You're solving an equation with another equation, with another equation, with this is your final equation, and it happens to give you the answer. So when you start with your quadratic equation, I don't want to see anything here except another equation, the beginning of another equation. And now you can use a bunch of equal sign after this. But when you solve an equation, you always solve it with another equivalent equation. And here's the equivalent equation. It is the opposite of b, which is going to now be a 6, plus or minus the square root of -6 squared, which is 36. And now this is the only place I throw in a little Kavanaugh'ism. I always put brackets there. And that's so that this subtraction sign doesn't get mixed up with whatever the sign of this number is. And that happens sometimes. So you do 4 times a, which is 1, times b, which is -7, all over 2 times a. X equals, let's see what we have here. 6 plus or minus the square root of 36, and now you have a -28 under there in the bracket. So you see, you don't want to have this subtraction sign and this negative sign be confused for being each other. They're two separate entities. Over 2. And now this equals 6 plus or minus the square root of 36 plus 28 all over 2. So x equals 6 plus or minus the square root of 64 all over 2. And the minute you see that, you go, whew, nice and easy, no i's, no negatives, and you don't have to simplify it and keep irrational numbers. You can just say 6 plus 8, or 6 take away 8 all over 2. So that gives you 2 answers. That gives you 7, and that gives you -1. So 7 and -1 are your answers. If you put this in my math lab, you put -7 and -1 first and then the 7. The minute you get answers like that, if your answers are rational numbers, that tells you, hey, you could have factored that original equation. It's only when you get irrational numbers here or complex numbers that you could have never factored what you started out with. So you got quite a few to work on in your class activity. Use your hands or your flags. Your flags aren't out, so just raise your hand if you have any questions, and I'll help you out with whatever you need, or maybe your table mates will help you out. That's even better. Hey.